Hello, my name is Kevin Gibbard, and I am a research professor at the University of Colorado in Boulder. I have been at CU Boulder since 1992, and I was a research faculty member in the aerospace department through 2013, which I moved to the computer science department where I am today. Today, I want to overview sponsored research activities related to NSF spectrum sharing, both for SWIFT, the Spectrum and Wireless Innovation for Future Technologies program, and for SciNRDZ, the Spectrum Innovation Initiative National Radio Dynamic Zone program. The SWIFT and SciNRDZ project activities are a collaboration of faculty and researchers from the University of Colorado in Boulder, from UC Berkeley in California, from the Hat Creek Radio Observatory in Northern California, which is managed by the SETI Institute, where SETI is the Search for Extraterrestrial Intelligence, and also unfunded collaborators, including Google, DeepSig, along with the University of Utah, and Virginia Tech, including the VT Commonwealth Cyber Initiative located in Arlington, and Virginia Tech located in Blacksburg, Virginia. One of the primary strengths of our combined group is our collaborative team. All entities and individuals, faculty, graduate students, and national lab researchers have directly contributed to the efforts involved in the three spectrum sharing projects. I would like to spend 15 minutes on this slide and regale the audience with the significant contributions from the different team members, but time constraints will not allow this personal digression. However, two specific unfunded collaborators from non-university entities deserve special mention. First, Google, via Andy Clegg, who is the Chief Technical Officer of WinForum, which is the organization that provides specifications for Citizens Band Radio System, aka CBRS. Andy has worked with Google to allow our team to test and verify terrestrial CBRS sharing for a dynamic protection area, also known as a DPA, around the Hat Creek Radio Observatory in Northern California. Please note that our team interfaces with the non-production Google Test Spectrum Access System, or SAS. We never interface with the Google Commercial Production SAS. Then this collaboration is significant as one, CU Boulder has very strong ties to the NIST campus, which is located 1 mile from CU Boulder. And NIST has actively developed RF sensing devices that are similar in functionality to those developed at CU Boulder. CU Boulder worked in parallel with NIST to design, implement, and calibrate our inexpensive software-defined radio-based RF sensors. We have made both the hardware design and the software open source for research community utilization. The video and demonstration in this activity are based on the efforts and results of three NSF spectrum sharing activities. The first is NSF SWIFT passive and active spectrum sharing, with the primary goals of initiating a collaborative relationship with the National Radio Astronomy Observatory, in this case, Hat Creek Radio Observatory. This is really a level 0 requirement to form this collaboration. The design, implementation, testing, and verification of RF sensors based upon modern, inexpensive software-defined radios is the second primary activity. The creation of an online available RF open dataset repository for community utilization is an additional goal, although not discussed in this particular video. The second sponsored project is NSF HCRO NRDZ, or the Hat Creek Radio Observatory National Radio Dynamic Zone Prototype Project, with the goals of developing an overall system architecture for dynamic protection of Earth-based radio astronomy observations from terrestrial or surface-based radio frequency interference, RFI. Importantly, RA facilities are not able to hide from satellite interference. Primary activities in this award include the development of a SAS, a spectrum access system, initial deployment and testing and interfacing, and the development of satellite orbit prediction processing software for dynamic protection of terrestrial RA scientific observations. The third sponsored project, Radio Astronomy Dynamic Satellite Interference Mitigation and Spectrum Sharing, aka RADASYS, focuses on the implementation, testing, and verifications of protection of Earth-based radio astronomy observations. Both terrestrial and satellite-generated interference are protected are protected in this scenario. Here you see a top-level functional block diagram and concept of operations. The problem here is spectrum sharing between passive and active systems has not been well researched. Deployed methods of spectrum sharing require some means of detecting whether a radio frequency band is being actively used. Passive systems do not transmit, so no means are available to detect over the air whether a passive system is operating. Currently, passive systems are protected by prohibiting all transmissions in specific frequency bands, requiring coordination with other services, or by designating geographic radio quiet zones within which transmissions are prohibited at all frequencies. However, increasing numbers of wireless devices are believed to be increasing the levels of ambient RF noise. Further, the increasing demand for spectrum is forcing more spectrum sharing between disparate radio services. New and innovative means are required to enable coexistence of passive and active services while making more spectrum available for the increasing number of active users. Additionally, to maximize the effectiveness of sharing and to protect the interest of both communities, the spectrum sharing mechanisms must be dynamic and secure. This overview and operational demonstration focuses upon the integrated system of subsystems and functional operations to meet radio astronomy spectrum sharing goals. Starting in the lower left, the radio frequency sensors provide RF IQ data from 70 megahertz to 6 gigahertz and are deployed on the HCRO observatory. Long-term RF baseline surveys have been conducted from 400 megahertz to 1800 megahertz and 20 megahertz bandwidth to establish the baseline noise floor level across each band. When not performing longitudinal RF baseline noise floor data surveys, the RFS sensors are utilized to perform real-time RFI monitoring and alerting for RA operations personnel. If an RA observation is in the CBRS band of 3500 to 3700 megahertz, CBRS spectrum sharing functionality is employed. CBRS CBSDs, which are citizens band transmitting devices, aka Wi-Fi access points, are specified in the FCC ULS database, and an NTI specified methodology is utilized to calculate the surrounding dynamic protection area, or DPA, for the RA facility. The maximum interference tolerance of the very sensitive RA antenna feeds is computed based upon standard ITU specifications. A primary focus of this research is to protect radio astronomy from potential RFI resulting from overpassing satellites. Orbital satellite ephemeris, which is the satellite orbital specifications, are typically known as these orbits must be managed. Satellite orbit prediction processing can identify all known satellites that will pass over a specific geolocation, e.g., HCRO, for a specified time duration. This information can be utilized for two important applications. One, satellite orbit prediction processing, SOPP, can optimize, e.g. minimize potential RFI from overhead satellites at an RA facility for a specified celestial observation. Two, the inverse can be computed, e.g. SOPP can identify precisely when a specific satellite will cross the main beam of an RA antenna. This is known as satellite spotting. The satellite orbit prediction processing system can generate a standards-based TARDIS-3 spectrum reservation to automate the RA observation. The Hat Creek Radio Observatory is located in Northern California, east of Redding, a very beautiful area. HCRO is located on the valley floor. Ancient lava flows and ranch land surround the facility. There are 42 telescopes, each with a 6.1 meter dish. Together, these 42 telescopes are known as the Allen Telescope Array, or ATA. RA observations can be made with a single antenna, arrays of several antennas, or all antennas can be combined. RFS sensors are deployed throughout the HCRO site for RF baseline surveys and for RFI detection and alerting during an RA observation. This is a summary of the subsystems involved in integrated spectrum sharing. The caveat here is that all subsystems have been designed and developed by the collaborative team. Truly, each subsystem easily deserves its own presentation. Several subsystems are the subject of recently published papers. This is a functional block diagram of the network topology and data flows between HCRO and CU Boulder. Note, due to the extremely high volume of RFIQ data generated from the RFS sensors, this architecture must be properly designed. CU Boulder is designing and testing a zero trust architecture, or ZTA, for proper security. This includes hardware security implemented on the RFS devices, e.g. Zimbit, proper authentication and authorization for access control, and encryption for data privacy security concerns. The RFS sensors include antennas, front-end RF circuitry, inexpensive software-defined radios, and are all enclosed in a custom-designed EMI protection enclosure to prevent any sensor EMI or RFI from escaping into the environment and potentially corrupting the signals of interest for an RA observation. This is a quick functional block diagram of the RFS software. Note that the RFS hardware specifications and acquisition software are available as open source. The RPI testbed, where all RFS software and hardware is configuration managed and deployed first in the CU Boulder testbed before deploying anywhere operationally. The RFS sensors are permanently deployed at HCRO on the ground. In August of 2022, the RFS sensors in a suitable EMI enclosure was flown on a UAV platform to perform aerial surveys to compare with ground-based RFI from a three-dimensional perspective. For an observation in the CBRS band of 3550 to 3700 megahertz, the dynamic protection area radius is computed per WinForum and ITU specifications. For HCRO, this turns out to be 112 kilometers for Category A devices and 144 kilometers for Category B devices. This is a functional block diagram of a key piece of software or software package of the satellite orbit preprocessor. Inputs are the orbital ephemera from multiple online sources, the specifics of the RA observation, including date, time, location, and observational frequency. Outputs include a list and associated graph of observational windows that are characterized by the number of interfering satellites above the observation, thus in view of the RA telescopes, and the number of potentially interfering satellites across the main beam of the RA antennae. When the RA scientist chooses the desired observation window, this information is encoded into a standards-based Telecommunications Advanced Research and Dynamic Spectrum Sharing Systems, or TARDIS S3 for short, spectrum reservation. Similar to the WinForum supplementary database for CBRS to augment the FCC ULS database, it is necessary to supplement the primary online satellite databases, all of which are incomplete, with additional satellite information from multiple sources. The TARDIS S3 specification format is shown on this slide. This is augmented, as you can see at the bottom, highlighted in blue, with satellite-specific information and forms the TARDIS S4 implementation, which is specifically augmented for satellite spectrum sharing. As previously mentioned, SOPP, the Satellite Orbit Prediction Processor, after computing a window, will send the TARDIS S3 or TARDIS S4 formatted spectrum sharing reservation to a spectrum access system for spectrum sharing coordination. This is the standards-based WinForum spectrum sharing architecture for CBRS, which includes the CBSDs, which are citizens band broadband radio service devices. They are really Wi-Fi access points. And it also includes ESCs, which are environmental sensing capability. ESCs are not overviewed in this presentation. A specific implementation of the WinForm specification is the Google SAS functional block diagram. Along with the commercial Google SAS architecture, our demo will integrate with Virginia Tech or VT Open SAS architecture shown on this slide. To set context, a CBSD nominal life cycle is shown for communication with a spectrum access system. Importantly, note the sequence of device registration, spectrum availability inquiry, spectrum transmission start, CBSD heartbeats to indicate keep alive, transmission termination, then relinquishment of the spectrum grant, and then device deregistration. Our RFS dashboard, which has information from the RFS sensors deployed throughout HCRO, performs RFI alerting and additionally RF analytics. These are used to monitor for any RFI in the RA observational band of interest and alert operations personnel of any detected RF activity that may be harmful and would corrupt the observational data. This is a demonstration of an HCRO RA observation in the CBRS band of 3550 to 3700 megahertz. The network topology is that the Virginia Tech Open SAS server is running at HCRO, and the CBRS CBSDs, which are really Wi-Fi access points, are located on the HCRO site. The window on the left is directly logged into one of the HCRO CBSDs. The window on the upper right is logged into the HCRO server running the Virginia Tech Open SAS server. The window on the bottom right is utilized to set a spectrum reservation for the HCRO telescopes. A CBRS CBSD can request a spectrum reservation, e.g. be an operational Wi-Fi access point at any time. Currently, in this scenario, there are no active spectrum reservations at this geolocation in any CBRS frequency channel. As a result, a CBSD should be able to request a spectrum grant and, if successful, can start to transmit on the assigned CBRS channel. Per the WinForm CBRS specifications, a successful reservation will require CBSD registration to the Open SAS server, followed by a spectrum inquiry for available channels, a grant request after which the CBSD can actively transmit, periodic heartbeats to the SAS server. When the CBSD stops transmitting, a grant relinquishment message is transmitted to the SAS server, and then the CBSD will deregister. The CBSD activities are logged in the window on the left, and the corresponding Open SAS server activities are logged on the right. In this case, since no spectrum grants are active in the CBRS channels, it is expected that the CBSD successfully receives the grant request. So we've started the CBSD spectrum request. You can see that it does the registration. You can see that it does the spectrum inquiry. It gets the grant. It starts the heartbeat. In the upper right, the VT Open SAS server has accepted the grant and provided the information. And now, after one heartbeat, the CBSD has relinquished the grant and has deregistered. Let's examine what happens if an existing spectrum reservation for an RA observation is placed in a CBRS channel. The RA observation spectrum reservation is sent to the SAS in the standard TARDIS format shown in the upper right. The reservation itself is shown in the bottom right. I just updated the spectrum reservation to start at 10 after the hour and end at 11 after the hour. We will copy this reservation to the Spectrum SAS and see how the activities proceed. It is 9 after the hour, and I will take and copy the spectrum reservation for the open SAS to ingest. Nothing is going on at this particular moment. So the next time this reads it, it sees that a reservation has been requested. It's now 9 after the hour. And at 10 after the hour, the reservation should go active. So right now, there we go. The reservation has gone active. The dynamic protection area is now operational, and there's a 1-minute spectrum reservation in this particular channel. So at this point, if we try and run a CBSD, this channel is reserved, right? So now we start seeing that we get a grant conflict. There is an RA observation going on during this time, and all the CBSD can do is stand there and retry until the reservation is completed. So what we can watch here for just a few seconds is the server continues to monitor for CBSD request. It's still 10 after the hour. And the CBSD on the left is just continually every 5 seconds looking to see if it can receive that grant request. So now we hit 10 after the hour, and the CBSD was able to get the grant request and begin the spectrum inquiry, and then get the heartbeat request. So once the spectrum reservation expired, the CBSD can properly use the spectrum. So please note the layout of the screen has changed. I now have connected into CBSDs that will connect to the Google SAS server. Since the BT Open SAS and the Google SAS are WinForm compliant, we expect the exact same results if we interface to the Google Test SAS instead of the BT Open SAS. In this scenario, we do not have remote monitoring capabilities for the Google Test SAS in the upper right-hand window, as you might imagine. But from the client perspective at the CBSD, we should see the exact same results. To optimize demo video length, I'll just show a CBSD interfacing to the Google Test SAS and successfully requesting and receiving a spectrum grant. All other functionality has been verified. So now we're actually connecting to the Google SAS and Google infrastructure, not to the BT Open SAS running on the HCRO information. So we get the spectrum inquiry. We can see things are slightly slower in response. We send the grant request to the Google Test SAS. We've got the spectrum inquiry. We got the grant request. Now we're going to start heart beating. And in this particular case, the heartbeat interval is set to 60 seconds. So you can see that we've interfaced with both the BT Open SAS previously and the Google Test SAS. All of this functionality has been verified. I'm going to pause the video in this particular instance just from a link perspective. So the previous couple of activities verified that CBSDs could properly connect into a Google Test SAS or into the Virginia Tech Open SAS to coordinate an RA spectrum reservation in the CBRS band of 3550 to 3700 megahertz. Now I would like to show how we attack the more general problem of protecting radio astronomy from overhead satellite RFI. SOPP, which is an abbreviation for Satellite Orbit Preprocessor, is the software developed for finding optimum in the sense of minimizing satellite RFI for an RA observation for the SWIFT and the NRDZ projects. In this scenario, an HCRO radio astronomer desires to observe a celestial object from 1000 to 1500 local time, which is PDT at HCRO. The coordinates of the celestial object are specified in a configuration file. The RA observational frequency is 135 megahertz, and the SOPP package determines the optimum reservation windows for the geolocation, which is HCRO in this case, and for the specified RA observation frequency. SOAP outputs include a list and associated graph of observational windows that are characterized by the number of interfering satellites above the observation, thus in view of the RA telescopes, and the number of potentially interfering satellites that cross the main beam of the RA antenna. The information provided by SOPP can also be utilized for satellite spotting, which is a method for accuracy verification of the SOPP analytical predictions. In this analysis, SOPP predicts that the MEDOP-B satellite with a downlight frequency of 135.0 megahertz will cross the main beam of the HCRO ATA antennas at 1419. When the RA scientist chooses a desired observation window, this information is encoded into a standards-based Telecommunications Advanced Research and Dynamic Spectrum Sharing Systems, or TARDIS-S3 spectrum reservation. I want to show now how SOPP can be used for satellite spotting, and this is a way of verifying the accuracy of SOPP. On Monday, the 24th of April, so just a week and a half ago, our team utilized SOPP to predict when a satellite that downlinked in the 5 gigahertz band would cross the main beam of the HCRO ATA telescopes to test the predictive accuracy of the software and integration with an operational RA facility. This is the real goal. The satellite chosen was the Sentinel-1A satellite, transmitting at 5405 megahertz or 5.405 gigahertz. Shown are the actual results of the HCRO ATA observation from the RA scientists. These are encouraging. Note that we are off by approximately 58 seconds from the peak of the time series. This can mean that our time calculations may be slightly offset, but we also don't know the exact behavior of the satellite. Resolving the time offset in future research will be a priority. This was the first time we tested the entire operational system, so it is encouraging, but this is research and there is still work to be done. There's lots of forward work such as that in these research activities. I want to talk about a couple of activities that we're collaborating on with other entities that we're looking to do in the future. The first forward work is NRDZ active transmitting low computation power control, and this is done with Utah. The background here is that the NTIA specified methodology for determining aggregate interference, especially in CBRS, between active transmitters and receivers is quite complex and certainly not amenable to dynamic real-time coordination. The University of Utah is developing a subsystem to coordinate multiple active transmitters in an RDZ that facilitates multi-user sharing by dynamic low computation power control. This would be a very interesting experiment in an RDZ. Even with an RA telescope, as the RA user would serve as the very sensitive passive receiver to protect from the active emitters. We can also use the CU Boulder radio frequency sensors or RFS devices, honestly, for satellite detection. CU Boulder has performed the analysis to detect satellite transmission with our inexpensive SDR-based RFS sensors. The link margin analysis shows that there is ample margin with this system, and we should be able to detect easily a satellite transmitting signal, such as the Sirius XM FM6 transmission. Another piece of forward work is the deployment of an RFS-based RFI geolocation system, which is very interesting. The inexpensive RFS sensors can be utilized in a sensor array for coherent RF sampling. This system has been proven to be operational in our CU lab settings. The advantage of the low-cost system is that the RFS sensors, which are utilized to detect RFI upon the HCRO telescopes, would be able to not just detect the incident RFI, but also accurately geolocate the source of the RFI, which will directly assist in enforcement activities related to eliminating rogue transmitters. So for our SciNerds current project with Radisys, the focus is on a LEO satellite spectrum sharing architecture. Our collaborative team is excited to extend the Spectrum Access System, or SAS concept, of coordinating geospatial temporal frequency sharing for the SciNerds Radisys project to protect passive Earth-observing LEO satellites. We look forward to presenting progress on this activity at NRDZCOM2. And for the wrap-up, please feel free to contact any member of our collaborative team and visit our website at the below URL for additional information, including hardware specs, open source software, and directly related research publications. Thank you.